All right, and so now at this point, after we have studied hopefully closely enough how to find the local maximum and local minimum of a two-variable function, then allow me to introduce the problem number 4 over here. So now on the same function, given that f of x comma y equals 2, and we're looking at 8x minus 8y over 8x squared plus 8y squared plus 1. So in this function we know that we can reduce this function down to f of x comma y. It reduces down to f of x comma y to be easier form, x minus y over x squared plus y squared plus 1/8. So even though having a small fraction here in that denominator, but a form like this is going to be a little easier for the calculation. Okay, but now allow me to bring in problem number 4 as following, and I'll call that example 4. Okay, and so we have found previously throughout the 3 examples we have done earlier that we found the local maximum and local minimum and all that, and critical points, right? For this function. So now I want to say find the absolute maximum and absolute minimum value of the function f of x comma y. But then inside the region G equals all points x comma y satisfying that x is less than or equal to, greater than or equal to -1, less than or equal to 1, and y is being the same, greater than or equal to 1 and less than or equal, greater than or equal to -1, less than or equal to 1. So this is our problem number 4 that I would like to introduce right here. So, and of course, as we will progress through this problem number 4 right here, we will have an explanation of, we will have a definition of what it means by the absolute maximum and absolute minimum. Okay, and so the terms to be really highlighted here is this: absolute maximum and the absolute minimum value of the function. So we have seen on the graph earlier on this function that after we've done the first 3 examples, then this is a local maximum. Down here was a local minimum. And these we located these at the critical points. So those critical points, we calculated those throughout the earlier examples. But so now, the reason we call these local minimum and local maximum simply because, hey, yes, we know that this guy here, this point here hits to a high peak, but in the end we did not see the entire graph for all its entire domain right here. So isn't this really the absolute maximum, meaning the real highest value, or there may be some other peaks out there that this portion of the graph didn't reach to? And that's the idea about absolute maximum right there. So what we found throughout the critical point was a local maximum, because we know that it was true being a maximum in a local area. That's why, back to the definition I brought up earlier, it was in a disk, in some disk around that critical point. So it's local. But now we want to find, hey, aside from that local maximum, will there be, and the local maximum itself can also be eventually may also qualify to become an absolute maximum. But well, now what I'm talking about is what about throughout the entire graph, throughout the entire allowed domain right there? Was that point, was the local maximum that we found also a an absolute maximum, or the actual absolute maximum is being somewhere else, located at a different point. And that's what it is. So basically, it's a maximum, but we want really the highest out of all maximum, because some peaks may be higher than the other peaks. Okay, and so we want to look for the highest maximum. So similarly, absolute minimum. On the picture, yes, we found a local minimum here, and that was a local minimum. And of course, the picture we're seeing here does not show the entire graph yet, and it will never show the entire graph of the whole function. So we want to know, outside from this limited viewing window of our graph right here, will there be another valley that's even lower than this? Or is this really the lowest one that we already reached already? And that's why we want to bring ourselves into this kind of problem. We want to lead ourselves into looking for the absolute minimum. Okay, so local minimum can be, there's a valley, there's maybe a lower valley, and so many valleys. We want to look for really the lowest valley right there. And that's basically what absolute minimum is. But so now allow me to swing over to the computer station and bring in an actual formal definition right here. And I will get to this domain. I will get back and explain what's going on with this being inside of a region D that's located in here. Okay. All right. So now here's my definition, and here's our definition right here. So in a closed, and I got a couple terminologies here being printed in boldface right here. In a closed and bounded region, a function f of x has an absolute maximum at some point a comma b if everybody else, if f of x at any other value x comma y has to be less than or equal to the function value at f of a comma b. So if we found that at a comma b we have an absolute maximum, meaning the every other point, see, for all other points x comma y in this closed and bounded domains, the function value there got to be smaller than or at most equal to the function value at a comma b. And that's the definition for absolute maximum. And so similarly, we're going to say in a closed and bounded region D, a function f of x comma y has an absolute minimum at some particular point a comma b if we satisfy this inequality. That's the function at any other x comma y value must be greater value or at least equal. See, that's why it's saying at least right here, at least equal to the function value at a comma b. Okay, and then that's for all x and y in D. Okay. So anywhere else aside from a comma b in this domain right here, then we have the function value being above that. That's what it means by being an absolute minimum at this point. But then now let's break down this definition a little bit more closely, one by one right here. So let me start with the idea of what it means by closed and bounded region right here. And so that's where I need to now start explaining about this region. So, well, the region here, we have had some lessons about how we understand a region on the x and y floor right here. So right out from this description right here, notice how the inequality has equal signs coming along with that. So I'm going to swing over to the other board. So the region, according to the region description that we have seen, it's all of the x and y pairs satisfying that x value is greater than or equals -1 and less than 1. So that's one first part of the description of the region, meaning, so now think about, this is the x and y floor, but we're looking straight down to the x and y floor. Then x values being anywhere from -1 to 1. -1 could be here, 1 could be here. And so we got a region. But now we do include the two ends right here. That means it's solid lines here. The two vertical solid lines being parallel anywhere going from -1 to 1. And now on the y-axis, okay, on the y, and so of course for now the region is being shaded between the two the two vertical lines here. But now, as another piece of information, the y value is being also anywhere from -1 to 1. meaning on the floor here, the y-axis, along with the y-axis. 1 is up here, -1 is down here. So now we're looking at only in between these. And we do include the 2 boundary points here. Okay, so a region like this that we have in our problem right here is called, a region like this is called a closed, because it's including the boundary. That's what closed means, okay? And it's bounded, okay? It's closed and bounded because the value is being all just completely contained inside of this. There's no other values going out there. There are regions. Now the concept of being bounded versus unbounded regions, I won't be able to give a clear definition here at our level of learning, but when you arrive at a higher course in math, there will be a much better definition of what it means by being a bounded region. But so here, this picture right here is bounded, so everything is contained inside, versus think about the entire R2 regions, everywhere is floating out. That's an example of an unbounded region right here. Or you may have something like this, like a, we may want to just take the 1 quadrant of the whole R square, but in the end it's still unlimited out there. So something like this is an unbounded. But something like this, yes, it's closed because the boundary is included, okay, and it's bounded. So this region right here is right in our problem, right in our example, describes what it means by being a closed and bounded region like that. Okay. All right. So now the idea is like this. Think about our function, or think about any other function. I don't want to rushly bring up our function yet, but just think about any function. Okay. So a function like this, right? By looking through the eyes right here, we have a critical value right at 0, 0. Okay. And this function here, yes, we will eventually say we have a local minimum right here. But now think about this function if we restrict that into a region. So let me bring in a region similar to the one we brought into the example. Let's say the region anywhere from, okay, so now let me put it on right into the x and y floor over here. So if I put in the regions, that's between, for x values, okay, so these are y values between -1 and anywhere from -1 to 1, and x values anywhere from -1 to 1. The x-axis is going this way, the y-axis is going this way. And there's a region right there, closed and bounded. The boundary is being specified. Now think about this region right here. The function itself, before I restrict the region, the function has its own natural regions, and it keeps flowing out and flowing out. But now once we restrict our function into one particular region, then think about it this way. Before restricting that into a closed region, a closed and bounded region like this, then this function really, we can sense, and we didn't get to that formal problem yet, but we can sense that this problem will keep growing up, and this surface right here, this parabolic shape will just keep growing up and growing up without an absolute maximum. So something like this, without a restriction, right, we won't be able to find an absolute maximum because it just keep growing higher and higher. Whereas we do have a minimum here, and it seems like in this picture, it seems like if this is all it will ever get, then this value aside, this point right here, aside from being a local minimum, it will also eventually become an absolute minimum. But now, if we restrict our function to a certain region, now another story is told right here. Okay, a complete different story is going on right here, but now just within this region, okay, then there will be some points being peak, highest peak, okay, highest peak right here, and lowest peak, highest peak. And that's why, in that idea right there, the concept of absolute maximum and absolute minimum can only be done when you restrict your function to a certain domain, okay? And that's why back in the definition, that domain there got to be a closed and bounded domain. And so now anytime inside a closed and bounded domain right there, you should be able to find an absolute maximum and absolute minimum, okay? And so that I gave a brief explanation that, when anytime that you have a function, and then when we restrict ourselves into a closed and bounded domain, we should be able to find an absolute maximum and an absolute minimum. And that's what leads to the following understanding. We now have a theorem. So this theorem says, let f of x comma y be a continuous function on a closed and bounded region D in R2. Of course, so think of R2 here is like the x and y floor like that. So the first statement says, as long as our function satisfies being a continuous function on a closed and bound region D, then the function has both absolute maximum and absolute minimum on this region right here. Okay, so the first statement here is a way to guarantee that, just back to what I was saying earlier before I showed this theorem on the computer. Anytime that you are inside a closed and bounded region, it is guaranteed by that first statement of the theorem that you will be able to find absolute maximum and absolute minimum anywhere or somewhere inside of that region. Okay, now be mindful that since the region is being closed and bounded, that's why anywhere on that region, the wording, the precise wording that was saying on D right there, meaning it could be from the inside part or right on the boundary. Being right on the boundary is also on that domain right there. So, and that's why the next statement of the theorem is saying the extreme values occur either at critical points inside in the interior of the interior. See, closed and bounded region. Those points in here are called interior. Okay, and if you grab any standard calculus textbook, it will have a clear definition of what it means by an interior point. Allow me not to get too far into that definition here in this limited length of the video lecture here. Okay, but interior point means point inside. But again, read the textbook to have a precise definition of what it means by being interior. Okay, because pointing finger in here is still not clear. And then being on the boundary. Okay, and you will also have a precise definition of what it means by a point on the boundary. So there's always, when you have a closed and bounded region, you have a point, an interior point, and a point on the boundary. There's difference. Okay, but so now the theorem says extreme values occur either at the critical points in the interior of D or at some points on the boundary. Okay, so now think of that statement number 2 right there in the theorem. So statement number 1 guarantee that we should be able to find, and we will be able to find, absolute maximum and absolute minimum on this region, including the boundary. And that statement number 2 is enforcing that when you are calculating maximum and minimum value, don't only just focus on critical points. Because yes, critical points may also happen inside of this, but aside from the critical points, there may be also other values on the boundary that happen to fall higher than the value of the critical points or lower than the value of the critical points, giving a local minimum. So statement number 2 guarantee that in order to find all of the possible candidates to become the absolute maximum and absolute minimum, you got to search through all critical points inside of the interior and also on the boundary. That's what statement number 2 of the theorem is stating. Okay, and so now, how are we going to bring that into our problem? Okay, and so now, sadly, I had to put the picture away for now. And I'm going to produce a smaller version of the picture. Okay, the x and y floor, we have a rectangle like this. A square like that, right? Positive 1, negative 1 on the y-axis, negative 1, positive 1 on the x-axis, right? And this is our closed and bounded region right here. Okay. From example 1 up to example 3, we have already found critical points for this function, and that's the reason why it's good that we connect all of these 4 problems together as one big problem right here. So critical points for this function for our function f of x here, either the original version or the simplified version. We're looking at critical points. We found that throughout earlier problems, one of them at 1/4, negative 1/4. And another one was negative 1/4, comma 1/4. And so now these critical points are all located inside of that region. See, the x, the y value, the x value is between negative 1 and 1. The y value is also between negative 1 and 1. And anyone viewing the video lesson here should be mature enough in math to understand that the critical points fall inside of that. The same with this other critical points. Okay? And so now all critical points that we have found are all located inside of this closed and bounded region. But so now we don't stop the problem here. Okay, aside, see, according to statement number 2 of the problem right there, we need to also search for some other points, possibly giving maximum along this trace, along this trace. Okay, along this trace, along this trace, along this trace right here, and also along this trace. So in other words, we got 4 edges, and so we gotta search. We gotta search for all points on each of the edges here. On each of the edges, we're gonna have to search for all possible points that may cause some maximum, minimum on each of those edges as well. Okay, and so now I'm gonna have to really. It's a long process, but it's easy to keep track of. I'm gonna now start out with that first trace right here. So how about on that trace where y equals negative 1? Right? On that trace where y equals negative 1, this trace right here, this trace right here. All right. So think about our actual graph, a graph of the actual function right here. Okay. On that first trace, y equals negative 1. Let me bring that in. This is the curve right there. All right, and you can already see that we got some bent nature of that curve right there. See, this is y equals 1. I mean y equals negative 1. Okay, and this curve right here is limited between x equals 1 and x equals negative 1 as well. That's why it's only a short tracing curve right there. Okay, but so now with that curve, see, there's some bending up, so we got to search for what that value is, right, in order to give that high peak right there, and then later on we're gonna put them all together and compare. So now back to what I was in the middle of doing when y equals negative 1. Now y equals negative 1, we're going to substitute that into our function. So that's making our function become the following. It's a function of x, so x is still an independent variable and changing value. But y equals negative 1 is fixed, so our function becomes something like this, which is later on produced for us the following. See, y equals negative 1, so our numerator becomes x plus 1. Because y equals negative 1 and our function originally was x minus y, and y being negative 1. So think about, we substitute y equals negative 1 in each of these. All right. And so now I'm looking at x plus 1 over, now I have x squared plus 1, because after substituting negative 1 in the y square and square, it becomes plus 1 plus a 1/8. Okay, and so 1 plus a 1/8 will easily becomes 9/8. Okay, so we've come to a function in terms of x, one variable. We eliminated the variable. Okay, and so now on that, and just keep in mind that on this function, x is only taking account anywhere from negative 1 to 1, according to this restriction. All right, so now on that path right here, on that trace where y equals negative 1, we're going to start doing, we can call this some function f of x right here. Now only one variable, right? Being x plus 1, it becomes the f of x comma y becomes some f of x, right? And x squared plus 9/8 at the denominator. But then we start doing that f prime thing, okay, to find the critical value on this trace right here. So we want to find an x value giving us a horizontal tangent line, right, in between x negative, in between negative 1 and 1 for x. And so that's why I was doing all this. And so the work comes out minus 64x squared minus 128x plus 72 over x squared plus 9/8 all squared. Okay, and then in the later ones, I won't have to get too far into this detail. I just want to explain for you. This is the standard process right here. And so we're gonna set. Okay, we're gonna let f prime. okay, to equal 0. That means this entire f prime right here will be set to equal 0. But since the denominator here is already a non-zero quantity and positive quantity always, it leads to the following equation. We just lead to having minus 64x squared minus 128x plus 72 to equal 0. We really just, after setting the entire rational expression here, you can reduce that and simplify that down to just simply the minus 64x squared minus 128x plus 72, okay, equals 0. And then from this equation here, we actually solved for solving this equation right here. We end up with two values. The two values are minus 16, okay, indeed, minus 1 plus and minus square root of 34 over 4. Okay, minus 1 plus and minus square root of 34 over 4. But so now, two answers coming out from this equation. But remember, our x values is restricted in anywhere from -1 to 1. So in that reason, we only take the only possible critical value here is -1 plus square root 34 over 4. That's the only x value qualifies. Okay, so we found one critical value here, and so that critical value happens right on this trace where y equals -1. So y value equals -1 already been fixed. So now we found that on that point on that trace right here, we found x equals -1 plus square root 34 over 4 gives a critical value, okay, a horizontal tangent line. And one more time, let's swing back at the picture right here. Yep. So that point right here where it's swinging and seems like it has a horizontal tangent line right at that point. Right? That point is going to be y equals -1, but x equals -1 plus square root of 34. All right. So now I'm going to have to erase this work right here. And let's write down our list of values. So aside from the critical points, okay, so now we have found on the boundary, right? On the boundary y equals -1. We found a point -1 plus square root 34 over 4, comma, -1 for y. So that's a critical point on that boundary, okay? Or it's just a point on that boundary giving a horizontal tangent line right on that boundary. And so now we got 3 other edges to handle. So now I'm going to move over to, and eventually I'm going to skip all the steps right here on that path where y equals 1. Okay? The function becomes, f of x comma 1. Right? That becomes x minus 1 divided by x squared plus 1 plus 1/8, which all eventually becomes plus 9/8. We got another function in terms of x. And then we do the derivative. And then we take the derivative. And so we take the derivative. Okay? And that leads us to a minus 64 x squared plus 128x plus 72 divided by all that x squared plus 9/8 all squared. Okay, and then so setting this derivative to equal 0. Okay, we're going to lead to it now, so allow me to start. You've seen that argument I've made earlier, similarly to that. So now I'm going to lead to just having minus 64 x squared plus 128x plus 72 set equal to 0. So the whole thing here was initially set to equal 0, and that reduces down to this. And that leads to our equation here. Again, this equation, solving it will come with 2 solutions, but only one of them qualifies x value anywhere from -1 to 1. And so the actual value, the actual accepted value for x coming out is x equals, so I found on that path right here, on that trace right there, x equals 1 minus square root of 34 over 4. All right, 1 minus square root 34 over 4. That means now I have another point to put in. So I have just now taken care of another trace right here. So on this edge, y equals 1, I found 1 minus square root 34 over 4, comma 1 for y. Okay, so I found another value right here. So 2 more values aside from the 2 critical points. All right, and so now I'm going to switch over to, so we've done the 2 traces on the y values right here, y equals -1, y equals 1. So we're going to look at the edge where x equals -1 right there. Okay, x equals -1. So x equals -1 gives me the function becomes the following, -1 comma y. And the function becomes some function in terms of y. So we're looking at -1 minus y over 1 plus y squared plus 1/8. That's what the function becomes. But then again, 1 plus 1/8 here can be easily combined as a 9/8. So the entire denominator here comes to y squared plus 9/8. And then so that derivative, so now we're going to, this is now a function in terms of one variable. And so that leads to our f prime of y here becomes, once again, what I have now is minus 64 y squared, actually 64 y squared plus 128 y, okay, minus 72. And then we go over y squared plus 9/8 all squared. And then again, very similar, we're going to set that, we're going to let f prime of y right here equals 0. And so now I'm going to skip some further information, but that leads to, we found y value being solving this equals 0 right here. We come out with -1 plus and minus square root of 34 over 4. But again, the y value here we found 2, but on this trace right here, but the y value is limited anywhere from -1 to 1, anywhere from -1 to 1. That's why the only one that qualifies is a -1 plus the square root of 34 over 4. Okay, so now we found another value. So on that trace where x equals -1, we found -1 for x, comma -1 plus square root of 34 over 4. All right, so that's the third edge going on. So now I can skip all of that work and you can verify that. But on the edge where x equals 1 right here, you will end up with 1 for x, and the y value there is 1 minus square root of 34 over 4. All right, so we found these 4, I would see them as critical points as well, but critical points on the edges, those give horizontal tangent right on those edges, okay? And then together with the critical points throughout the whole region right here, right? The critical points giving horizontal tangent planes. These are critical points giving tangent lines on the edges, and then these are critical points giving horizontal tangent planes throughout inside in the interior. Now one more thing. See on the edges, on the boundary of the picture. So now back to the graph. I put all of the 4 edges there, and now you can see there's a better picture. See? These are all the 4 critical points that I was talking about on the edges. And so now, but then these corner points count too. These intersection points where the edges meet, they count too. So we got 4 of them. And so now I'm going to put on the list. I'm going to put among the list right here 4 other points. So I got 1 point here as being at 1, 1. That's where the 2 edges meet it, 1, 1. And then there's another one right here, 1 comma negative 1. We got to check the function value at that point too. And we got, there's another one here, negative 1, negative 1. And we got another one here, and the last one here, yes, negative 1, comma 1. So now for this function, after restricting that into a square region like that, or a square region like that, then we got 2 critical points in the interior, 4 points found among the edges, and including with the 4 corner points right there. All right, and so now it's just a matter now at the next step, after tracking down all of these special points right there, all of these critical points and points on the boundaries, including the corner points right there. Okay, now we're going to put all of these. So these guys right here are corners. All right, so these are the corners. So now we're going to put all of these functions values, right? All of these points evaluated into the function, the actual function. So now I'm talking about, we're calculating, now I'm running short of board space right here, so allow me to do the following. So for the critical points, I will evaluate f of 1 comma f of 1/4 comma negative 1/4. I will also evaluate f of negative 1/4 comma 1/4. I will evaluate now f of negative 1 comma square root 34 comma 1. I mean comma negative 1. I will also evaluate the function value at this point. So we already knew the values for these from the earlier problems right here. Okay, but let's come down with these. And so I will evaluate the function value at all of these other points that we found on the boundaries and at the corners. And so f of 1 comma 1, f of 1 comma negative 1, f of negative 1 comma 1, and f of negative 1, negative 1. So let's obtain the values for all of these points right here. But these are the points that's at the corners, and we substitute all of these points that we found into the beginning functions. All right, and so in that way right here, allow me to swing over to my computer to obtain some values right there for that. And so we have already learned from the earlier problem. This value right here will be equals 2 for that. Okay, and this value here will be equals negative 2. So we got those values. All right, and this point right here, I got approximately about positive 1.09. Okay, and this one of mine here is a negative 1.09. All right, according to my calculation right there. And then up to this point, according to my calculation on the computer screen, I have negative 1.09 as well. Okay, and then this point right here, positive 1.09. Okay, and now we're gonna look at the values for these corner points. Okay, so these corner points are here, 1 comma 1. All right, I'll be looking at this point gives me 0. Okay, and then the next point here, 1 comma negative 1. This point gives me 0.94 as the function's value here. Now negative 1 comma 1. This point here gives me negative 0.94, and this last point here, f of negative 1 comma 1. This point gives me 0. All right. So now with all of these points with values came out right here, then now we can decide who's giving which one here is the absolute maximum and which one is the absolute minimum right here. So yes, these are how high, how low these points reaches. This one right here, right, we have that one right there is absolute maximum, simply because at that point the function value came out the highest, but in that domain, in that region, in that restricted domain right there. throughout all points again compare. This one here looks like it's the lowest value. So yes, we call this the absolute minimum. So we reach, in this domain, we reach absolute minimum at this particular point. All right. So the point of the lesson here is that anytime you are asked to find the absolute maximum and absolute minimum value, you have to look at the critical values inside, the restricted domain, and look at all of those points on the boundary possibly, and all of those points at the corners right there where the boundary meets right there. Okay, and for our kind of problem that we do in here, we are only at our level for our learning. We only learn how to look at absolute maximum and absolute minimum value on where we are provided with a closed and bounded domain right there. Now, I'm not saying that there are not problems like this out there existing where you finding absolute minimum and absolute maximum on an entire open domain. I'm not saying that those problems don't exist, but it will have to wait until a higher course to get through right there and to come up with a more universal method right here to find absolute minimum and absolute maximum without a restricted domain like this. So here we only focus on having a restricted domain, a closed and bound region. Yeah. And further, even on a closed and bound regions, okay, we are only limited, for this lesson right here, we are only limited to those closed and bounded regions where it's having edges, okay, edges that join together as a shape right here. Okay, so that we got on the boundaries, it's just a combination of edges. We didn't cover that, we won't cover to the kind of problem where, now let me swing back to this board right here. The same problem, but if I use a region like this, sort of as a nice one circle around right here, the problem will grow a lot harder. Okay, or generally, if we're looking at some general regions where it's looping around like this, right? We will have to wait for a higher course to learn some more universal methods to calculate, okay, the maximum and minimum, absolute maximum, minimum in the domain inside and on the boundary being a loop around general region like that instead of edges connecting, okay, and we will learn those in a very near course in the future like that, okay. But then finding absolute maximum and minimum for the entire open domain, we will have to wait until a much higher course in order to handle that, or wait until everyone is very mature in math, and we will look for different ways of finding that. But here we only limit to having a closed and bounded region, okay, and the regions come to a picture of either a square, a nice rectangle, a square with edges connected, or the most a triangle. All right.